Bismillah ar-Rahman ar-Rahim, as-salatu was-salamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Okay, so this is now lecture 3 from chapter number 4, integrating linear algebra with NumPy. And today we will talk about one of the most important aspects in linear algebra in data science, which is called the eigenvalues and eigenvectors. So as already discussed, many of you have already studied eigenvalues and eigenvectors in linear algebra, but from mathematical perspective. But now the question we try to answer today is why eigenvalues and eigenvectors are important and how do we need them in data science, okay, practical use cases. So let's get started. So before starting with this, we need to introduce the matrix vector multiplication. And you know, usually when we have a matrix, for example, n by n or n by m, and we multiply it by a vector, it will result in what? In another vector. And this vector, basically, the w vector is a transformed vector of v. So what does it mean, a transformation? In space, when you have vectors in space, usually what you can do, you can rotate the vector, you have a rotation, or you can scale the vector up and down. Okay, these are the transformations. So it will result into a different vector, usually both in rotation and also in the magnitude of the vector will be even bigger or smaller. So let's illustrate this concept. Now let's take transforming the vector orientation. Like in this plot, we have a vector and we transform it with a certain degree. And the magnitude is the same. So how does this happen? Usually this happens from a special type of matrix that we call the rotation matrix. And the rotation matrix is usually expressed by the cosine theta, the minus sine of theta, and here the sine of theta and cosine of theta. That's one of the examples of rotation matrix. And then you can apply theta, for example, to 45 degrees. So this is a matrix, it's going to have numbers. And these numbers will be just the cosine and sine. You know, here we have the cosine of 44 multiplied by this vector 1, 0. So this is the vector 1, 0. So what happens when I multiply this matrix by this vector? If I change these values, so it's going to result into the square root of 2 divided by 2 and the square root of 2 divided by 2. This is going to be the blue vector. So this blue vector, what does it represent? It's a rotated vector. So it's transformed. It was transformed. Why? Because it was multiplied by a matrix. So usually, what I want you to understand is when we multiply a vector by a matrix, it's going to transform that vector into a different vector. In this particular case, it was transformed only as orientation. It didn't change the magnitude. Why? Because the determinant of this matrix is equal to 1. So determinant means equal to 1. It means it's not going to scale up and down the magnitude. It's going to remain the same. And why the determinant is equal to 1? The determinant is the cosine multiplied by the cosine plus the sine multiplied by, or minus the sine multiplied by the sine. So this is going to be cosine square plus the sine square. By definition is equal to 1. And determinant is equal to 1. So this is an example of a transformation in space that is only rotation. It didn't change the magnitude of the vector. Is it clear? Okay. Let's look. There are other types of matrices that we call them scaling matrices, like this one. So basically it is a diagonal matrix. So what does this mean? Now, when I multiply any vector by this matrix, it's going to scale up every axis or every vector, okay, every component of a vector by a certain factor. Let's make this example here. Let's consider I have a vector v, 1, 1, like this one. Okay, so this is the vector v, 1 and 1. This is our vector. So this is 1 here and 1 here. It results into this vector. Okay, and I will take the scaling matrix with factor 2 in this diagonal and the factor 3 in this diagonal. So what will happen? I'm going to scale this number by 2 and I'm going to scale this number by 3. And this is going to result into the vector 2 in the x-axis and 3 in the x-axis. So it's again a transformation. Here it's both in rotation and also in magnitude. Okay, although it only scaled, look, it scaled only each vector component. So I scaled this one twice and I scaled this one 3 times, and this result into this vector. And the determinant here is 6, so it's different from 0. So here it has also changed the magnitude. And we can also multiply a matrix or a vector by a scalar, by a number. So what will happen in this case? Imagine that you have a vector x and y, and you multiply both x and y by alpha. Look here, we have multiplied x and y by 2 different values. And this is why the new vector was not in the same line of the first one. But if we multiply with the same value here, alpha x and alpha y, so it's going just to extend, stretch, okay? Or maybe squeeze the vector. If alpha is small, it's going to squeeze the vector. If alpha is greater than 1, it's going to extend the vector. And here I multiplied the value alpha by 3. So this vector magnitude is going to be 3 times the original vector. One question here. Is multiplication by a scalar change the angle of the vector? No, obviously. Okay, so what we have learned so far is that if I multiply by a matrix, naturally it can change the angle and also the magnitude. And if I multiply by a scalar, I won't change the angle, I will change only the magnitude. This is what we can learn so far. Now, why I introduced all of this is to get you an intuition about the eigenvalues and the eigenvectors. How is that? Look at this example here. We have a vector 1 and 1. And we have this scaling matrix. So this is our original example. So let me take now another vector. So when I took 1 and 1, what happened? It has changed this vector both in magnitude and also in the angle. Let me take another vector, this vector, 1 and 0. And I multiply this vector by the scaling matrix, it will result into 2 and 0. So I took this vector, I multiply by the matrix, and I get another vector that is only scaled. It was not rotated. And that's different from the previous examples, which has changed also the orientation. This particular vector doesn't change its orientation when it is multiplied by the matrix. So this is a very special case. Is it the only case? Let's try to explore. Now let's take 0 and 1. 0 and 1, it's this vector. And if I multiply by the scaling matrix, so 2 multiplied by 0 is 0. And 3 multiplied by 1 is going to be equal to 1. And look now, we're going to have this scaled vector. It doesn't change orientation, it's only changing the... so what does it mean here? So it means that S multiplied by V is equivalent to lambda or alpha multiplied by V. It's multiplying by a matrix is equivalent to multiplying by scalar. This is a very special case. And when we have this special case, the vector that satisfies this condition, we call it an eigenvector. And the value that satisfies this condition, we call it an eigenvalue. Okay? So eigenvalues and eigenvectors are special vectors and values that are rotation invariant. This means that the multiplication by the matrix doesn't change the angle of the vector. So they are special vectors and special values extracted from the matrix itself. If you have a matrix that satisfies certain properties, it will have certain eigenvalues and certain eigenvectors that satisfies this condition. Okay? So now we understand this general concept, but this has pretty much excellent application in AI and data science that we will discover. But you understand now the essence of eigenvalues and eigenvectors. They don't change when we multiply them by the matrix. So this means that every matrix, it has special vectors and special values such that the multiplication of this vector by the matrix is just a multiplication by the value of the vector. And this has a consequence that it doesn't change orientation, like we have found out this vector. Now, this vector here, 1, 1, is not an eigenvector. Why? Because when I multiply by the matrix, it will change both the orientation and also the magnitude. And we want the eigenvalues are those that doesn't change orientation, that do not change their orientation. We call them eigenvalues or eigenvectors. And every eigenvector, it has a particular eigenvalue associated to it. So why this 2 is associated to this vector? Because it satisfies this property. It doesn't satisfy the property 3 multiplied by v1. It's 2 multiplied by v1, and the second one, 3 multiplied by v2.
So 2 eigenvalues, sorry, the normalization of 2 eigenvectors will give me my original vector.
I didn't understand.
So I have these 2 eigenvectors, v1 and v2.
Mm-hmm.
If I normalize them.
No, you don't normalize. The eigenvectors are special vectors. If you normalize them, they will become different vectors.
So if I take the square root of if I take the square root of this sum of their squares.
Usually the eigenvectors are normalized vectors. Okay? And now what I want you to understand is that for every matrix, there are, of course, the matrix must satisfy some properties. We're going to talk about these properties. If it satisfies the properties, so it means we can find values and vectors such that this vector, when multiplied by the matrix, is just proportional, will be proportional to the magnitude of that vector. Okay? This is what we want to understand. And this has a very, very important properties that we will talk about them. Okay. So among the eigenvalues, there are some values that are bigger than others. So usually we need to sort them out. And usually in data science, we're going to look at what we call the dominant eigenvalues. So those dominant eigenvalues are the greatest numbers and will have the greater impact in terms of scaling, okay, along the different axes in the space. So for example, in our case, lambda 2 equal to 3, it corresponds to the largest value, and it corresponds to V2. So later on, when we talk about principal component analysis, it's an application of eigenvalues in data science, you will understand why we need to look at the dominant eigenvalue or eigenvalues. We usually sort them by their order. So this is pretty much used in one of the most popular techniques in machine learning. It's called principal component analysis. And this technique is used to reduce the dimension of the features in a data set. I'm not going to explain now, but I'm going to explain by the end of the lecture. But just to give you some flavor why we need these type of relationships. This slide summarizes all we have talked about, so you can look at this later on. Yeah.
How will we get the eigenvectors and values? The example we had earlier was simple, 1001.
Yes, I'm going to talk about how to find them, the algorithm to find them. Yeah, we'll talk about this. So let's look now at the formal definitions. The eigenvalues and the eigenvectors are defined by the equation, the matrix multiplied by V is equal to lambda multiplied by V, where V is an eigenvalue, is an eigenvector of the matrix, and lambda is its corresponding eigenvalue. This is the definition. So this is going to be converted into an equation system with lambda to find, and based on this we can later on find the eigenvectors. Yes.
So for corresponding eigenvectors and values, does the change in magnitude have to be equal?
The change of what?
The change
No,
in
no, no, no. It depends. At the end, we're going to have different lambdas that you will extract according to a certain formula. I'm going to tell.
So as long as the angle is not changed?
Yes, yes, yes. We will see the formula on how to find them. Now, for example, this is an example of a matrix A with these numbers. Using some algorithm we're going to introduce. First of all, we identify the eigenvalues. So usually an n by n matrix will result into n eigenvalues and n eigenvectors if they satisfy certain properties. And the corresponding eigenvectors, so this is eigenvector 1 that corresponds to the eigenvalue 1, and this is 2, and this is 3. Now, if you do this equation, AV is equal to lambda V, so it's going to be satisfied. This is the vector that results from the matrix multiplication by the vector, and this is also the values that result by lambda multiplied by V. So basically, they are exactly the same. And this is how we can do in NumPy. So in NumPy, you define an array A, NumPy array 4114, and then you can use np.linearalgebra.eg of A. So this is going to extract the eigenvalues and the eigenvectors, and finally you can visualize them over here. Okay, so the eigenvalues indicate the magnitude of the stretching, and the eigenvectors show the direction that remain unchanged under the transformation when we make a dot product with a matrix. Okay? So this is just a visualization similar to what we have talked about before for the previous example. Okay, so we have eigenvalue 1 is equal to 1, 0, which is this one, and it has an eigenvalue equal to 1. So they are exactly the same because the eigenvalue for the first vector is for the second vector is equal to 1. For the vector number 1, which is in blue, we have 0, 1, which is it's 0, it's 1, 0, 1 in the x-axis, and the eigenvalue is 2, so it's doubling the scale of the original vector. And this is a Python script on how we can do that. So starting from a matrix, which is this one, you can calculate the eigenvalues and the eigenvectors using linearalgebra.eg applied to A. So this is going to provide you all this information, the eigenvalues calculated, and also their corresponding eigenvectors. And look at the verification. If I multiply A multiplied by V is going to equal to lambda multiplied by V. We find the same numbers. Okay. So what are the characteristics of eigenvalues and eigenvectors? So let's look at the trace of a matrix. What is the trace of a matrix? The trace of a matrix, by definition, is equal to the sum of the diagonal. If you have a matrix A, so it's going to be the sum of AII. This is called the trace. So here, if I have two-dimensional matrix, it's going to be A11 plus A22. That's the trace of a matrix by definition. And if you find the eigenvalues, the magic here is that this trace is equal exactly to the sum of all eigenvalues. That's pretty much a strong relationship, property of the eigenvalues and the eigenvectors. The sum of the eigenvalues is equal to the sum of the diagonal of the original matrix. So it doesn't change the property of the matrix. Why we're going to use this? Because later on we're going to use the eigenvalues to diagonalize the matrix. So every matrix can be transformed into the diagonal matrix transformation. Okay. And this is an illustrative Python script. We have a matrix B, which is equal to this one, and you can calculate the trace of the matrix. So the trace of the matrix is 9. And then we calculate the eigenvalues. And we show the different, okay, here we calculate the eigenvalues of the matrix and then we will show all of them. So we have 6.0, 1.6, and 1.3. Making the sum of all the eigenvalues, we will find exactly the same value as the trace. Okay? And this is the mathematical numerical application. So this is a strong property of the eigenvalues in matrices. And the eigenvalues are not always real numbers. They can be complex numbers. Okay, so in this particular case, we have the matrix A. We have the trace, and look now, the eigenvalues of A is 9. This is a real number, 9.5, and this is a complex number. It's 1.7 plus 1.4 G. G is the imaginary part of a complex number. You know what is a complex number? Okay, so same thing here for the eigenvalue of 3, but the sum, okay, this is going to neutralize, all imaginary parts are going to neutralize, and the trace of A will be also the sum of all the eigenvalues. Another strong property of the eigenvalues is that the determinant of A is equal to the product of all eigenvalues. So determinant of A is equal to lambda 1 multiplied by lambda 2 until lambda n. And a matrix has a determinant different from 0. It means it's non-singular. So one of the properties of a matrix to have eigenvalues is to be non-singular. The determinant must be different from 0. And it makes sense because this product must be different from 0. Otherwise, the matrix is not invertible. So look, all this concept of linear algebra are pretty much correlated with each other. And this is an example here. So we have this matrix. If you calculate the determinant of the matrix, you will find 13. And if we extract the different eigenvalues, 6.05, 1.64, and 1.31 is going also equal to the same value of the determinant. And this is a NumPy script showing the application here. Okay. Any question? واضح? Okay. So as I already mentioned to you, not every matrix will have eigenvalues and eigenvectors. So the matrix must be square. That's the first rule. And it must be non-singular. What does it mean? What does it mean, non-singular matrix? The determinant must be different from 0. And it must be, this means that the matrix must be invertible. We can make the inverse of the matrix. If we cannot make the inverse of the matrix, we cannot have eigenvalues and eigenvectors. Okay? And the eigenvalues can be either real or complex. We made an example. So, and the property of eigenvalues and eigenvectors are applicable for diagonalizable matrices. It means that our matrix, that we can convert them into a diagonal matrix. And a diagonalizable matrix, it means A can be written as P multiplied by D by P minus 1. So what is D? Is the diagonal matrix of eigenvalues. And P is the matrix of eigenvectors. You take the first eigenvector, the second eigenvector, the third eigenvector. You multiply it by D, the diagonal matrix, and P minus 1, it's invertible. You're going to find the matrix A. This is what we call eigenvalue decomposition of matrices. وفيها استخدامات كثيرة في dynamics, control systems, and many applications. Okay? And there are other properties we can skip for now to focus on how to find eigenvalues and eigenvectors. كلامنا على كل شيء, لكن how to find them? What's the algorithm? Of course, now in NumPy, you just call a function, and the function is going to find you these numbers. But of course, there is a mathematical concept behind this. Is first of all, you need to find the eigenvalues. By solving the equation system, the determinant of A minus lambda I is equal to 0. What is I? Is the identity matrix, is the diagonal matrix with all ones. So it means you will have a matrix, all of lambda, A minus lambda diagonal matrix, the determinant of this matrix must be equal to 0. You will find the values of lambda. So you solve an equation system to find the eigenvalues. Look at, this is a simple example. You have a matrix, a two-dimensional matrix. We calculate determinant of A lambda I, so 4 minus lambda. This is 0, so it remains 2. 1, 3 minus lambda equal to 0. So I have a simple linear equation system over here that I need to solve. And solving this one by one, so I calculate the determinant, which is this quantity minus the product of these quantities by definition of the determinant. And then, doing some rearrangement, we have an equation system, quadratic equation system. This results into two values. This is why sometimes we might have imaginary number. If we don't have solution in the real space, we're going to have it in the complex space. So these are the two eigenvalues. We found them. Okay, now applying the same thing on Python, we're going to find also the same values. Now, when we find the eigenvalues, we can find the eigenvectors. How we can do that? So for now, each eigenvalue we will solve A minus lambda I V. And V will be the values that we will look for. We don't know what are these values, equal to 0. So it's another equation system that we need to solve. Like here, for example, 4 minus 2. So this is going to result into this matrix, 2, 2, 1, 1, multiplied by x and y. This is the unknown. Okay, x and y are unknown. So we apply for the first eigenvalue. We're going to find x and y, so x equal to minus y. Solving this, we will find the value of v1, 1 minus 1. Now we do the same thing by replacing lambda with lambda 2 equal to 5. And you're going to find the eigenvector 2 and 1. واضح شباب ولا نفسر؟ مفيد افهموا المبدأ العام. It's okay. These are equations, you can look at them. It's not difficult, by the way. Is this clear?
Yes.
This one?
Yes.
It's clear, okay? And this one, you need to solve this equation system for each lambda value. How many lambda values we have? 2. So I'm going to replace lambda by 2 here. And this is going to result in a linear equation system. And then I'm going to replace lambda by 5. And it results in linear equation system. And every linear equation system, we will find a certain value for x and a certain value for y. All these are computations. You can look at them carefully and you will realize how to calculate. Okay? You will not do mathematical calculation. This is supposed to be done in linear algebra, but just to show you the internal mechanics, how things work. We're going to use just eigen in NumPy, and you will find all of this. So this is the visualization of the eigenvectors. We calculated 2 eigenvectors, 1 minus 1 and 2, 1. And they are visualized as such into a two-dimensional plot. So what does it mean now? What's the meaning of these vectors? If they are multiplied by the matrix, they will be only scaled by 2 and the other one by 5. Not the whole thing. Okay? And later on we will use them. I'm going to show you now an application of PCA. They will be used as axis of projection. So it's like instead of having the XY axis, okay, we can have this axis to transform the data into different axes. We will see this just in a while. Okay? If you understand 60-70%, that's fine. Don't worry about it. Now, all of this is to understand how to use it in data science. And one of the famous techniques is called principal component analysis. And by the way, this is one of the most difficult techniques. I try to make things so simple. If you open YouTube and look PCA and eigenvalues, it's not that obvious. But we understand now we have a matrix, and this matrix can result into eigenvalues and eigenvectors. How this is used in PCA with data science. Let's start with a simple example. In data science, you will be given data set and later on make a prediction model. I want to predict the grade of a student. For example, a student with this grade in math, physics, and chemistry and English, what will be its possible final GPA? Okay? So consider this as input of raw data and you'll use them. So one of the techniques that you'll use, I will use all these features, the math grade, the physics, the chemistry, to estimate the GPA or to predict the GPA. That's one of the possible ways. But let's look at these numbers. Usually, the grades in math are somehow related to the physics. People who are good in math, usually they are good in physics. There could be some exception, but the variance should not be. Okay, so we have the data. When we have some data that is very correlated, what does it mean they are very correlated? Related.
There is a relationship.
Yani one, it means obviously the other. They don't make any difference. So I can consider only one of them. صح ولا لا؟ منطقيا يعني.
Just a question about the word correlated here in math science. Does it mean that there is a relationship?
Yes.
Either it's a positive or negative
Yes.
or opposite.
What is the correlation? The correlation factor between two random variables. If the correlation is high, if I have 100% correlation, it means they are the same. If I have 80% correlation, 80% of the time they are proportional. It's like a proportionality between the two quantities. Right? Okay. So usually in data science and in predictive models, we don't want to consider the features that are correlated. هذه قاعدة. It's like a rule. We want only to keep the features that have strong variance among them. واضح؟ لأنه if everything is the same, it's like you don't have any information. Information comes from the variance. اختلاف البيانات هو اللي يخليني لو نعطيك كل بيانات نفس الشيء يقول لك اعمل لي prediction. مثل هذا مثل هذا مثل هذا. You cannot make any prediction in the future. لكن if you have patterns, if I have this pattern and another pattern that is different, I can differentiate between patterns. If the patterns are the same, you cannot differentiate with the patterns. So the patterns are different when they have variance between them. When they are different. شفتوا المفاهيم بتاع probability statistics الآن كيف نستعملوها in a certain meaning. Okay? Variance is not just an equation that we can solve, it's a meaning. When we want to make predictive models, we want to keep the data that is relevant, that if I change this one, it's going to impact the model. Like, if you change the values and the model will be the same, so it doesn't bring any information. Okay? And the information is usually captured by the variance. تدرسوها في الانتروبي فيما بعد. ما أعرف الكلمة هذه سمعتوها من قبل ولا لا. لكن الانتروبي is the randomness of the data, by the way. So the randomness will provide us kind of patterns that try to understand in a model to make good predictions. Okay. So اتفقنا انه الآن we want to reduce these features to be only relevant. So the first thing when we have a data set, مثل ما قلت لكم data science, you need always to normalize. There are different normalization. I can divide by the maximum number grade, مثلا 100%, or this is called the mean variance normalization. We subtract by the mean and divide by the variance. It's going to give a value between -1 and 1. So we will normalize the data set instead of being numbers between 0 and 1. This is just to have a convergence of our analysis. So it will be values between -1 and 1 that you can control. This is standard normalization. And then we would like to see whether these grades are correlated or not correlated. The simplest way is to calculate the correlation matrix. What does it mean, a correlation matrix? Is the correlation between every two grades. على الداتا set كامل. شفت عندنا we have the whole data set. I can understand whether there are differences between the grades of the students. If there are no differences, most of the grade will be close to 1. The covariance will be close to 1. Okay, so the variance of math in normalized, or the variance of physics will be equal to 1 because we did normalization. But now I will be interested to see the covariance between two courses. And let's apply this. So this is the mathematical equation that you know already in probability and statistics. And we got this matrix. This is the covariance. What does it mean here? How do you understand this? based on the data set, 99% of the cases, the math grade and the physics grade is correlated. The correlation is a bit less for this course. Which course? This course is chemistry. And with English is less correlated. طبعا these are scientific courses. So they have strong correlation. يعني a little bit less. At the end, all these grades are pretty much correlated. يعني people who are good in math, they tend to be good in English, physics, and chemistry. This is how I understand it. This is a very extreme case, you know. And you will see now, with eigenvalues, how this is going to be reflected. You will see the beauty of mathematics, just in a while. Look at this now. We calculate the eigenvalues and the eigenvectors. What do you observe? Look at the eigenvalues. Does this tell you something? About how many independent features we will have. And when we have seen like this, are these features independent? They are strongly correlated. So all of them, it's like one of them. Look at this.
They are very much different.
Look at the eigenvalues. How many strong or dominant eigenvalue you have? One. Look, 3.9, 0.03, 0.00, you know, because it's like I have only one axis vector that is strong. It's all these features, they are like only one vector. I can compress them, project them into only one vector. Which vector to project? This one, the first. And by the way, you can choose to only consider this one. Now the number of vectors that you want to consider, it depends on how many dominant values you want to use. Okay, now how to use, so what does it mean, a projection of an ax is basically a dot product. Okay, look at this now. What we're going to say, what we're going to do, we have now determined our eigenvalues and our eigenvectors. And then we will take student by student. Now, instead of having a student represented by all these, by all the values, or by math, physics, chemistry, and English, we can make projection by multiplying. Okay, let's take this example here. I take the first student, which has the values minus 0.5, minus 35, minus 0.05, and minus 22. And I will multiply by the eigenvector. So this is going to give me another feature that represents the grade of student 1. It's called ZPC1. So I projected all these vectors into another vector. And we can do the same also for the second component. And finally, all the data set, instead of working with 4 features, I can reduce them to 1 feature or probably 2 features using the PCA. Okay? So that's it for today. Okay, we introduced eigenvalues, eigenvectors, and a sample application. We will come back to PCA when we talk about unsupervised learning.